We are discussing about other current sources or sinks. The two important current sources are Wilson current mirror and regulated cascode current mirror. Both are having negative feedback. So because of negative feedback, both have stable output currents and both have increased output impedances. We already discussed Wilson current mirror. Today we are going to discuss about regulated cascode current mirror. The advantage of regulated cascode current mirror over others are: first, stabilized output current; second one, output impedance is higher than Wilson current mirror; and third one is V naught minimum is least out of most current mirrors. So V naught minimum is least is nothing but this is the biggest advantage, so that voltage swing is going to be a large. Now we'll see how I naught is stabilized, and we will calculate R naught, and we are going to prove that one this is going to be highest and this is more than Wilson current mirror, and we will calculate V naught minimum required, and that we are going to proving that one it is the minimum possible out of all current mirrors till now we discussed. So look at the left diagram. Regulated cascode current sink. Regulated cascode current sink. There we are using 4 transistors M1 through M4 and 2 biasing voltages V bias 1 and V bias 2. V bias 1 is the voltage used to bias M1 transistor. V bias 2 is voltage used to bias M3 transistor. If you clearly observe the differences between Wilson current mirror and regulated current mirror, regulated cascode current sink, both are using the number of transistors same, and the configuration and the circuit diagram is going to be exactly same except one difference. If you observe M3 in Wilson current mirror, it is diode connected transistor. Diode connected transistor, that is nothing but drain and gate of M3 are shorted, and gate voltage of M2 is nothing but source voltage of M4. Source of M4 and gate of M2 are going to be shorted. In regulated cascode current sink also, gate of M2 is connected to source of M4. So this connection is not changed. Only the thing is M3, which was previously diode connected, now it is separately biased with external voltage. M3 is diode connected in Wilson current mirror is nothing but it itself provides biasing. There is no external biasing required since M3 is in saturation, it itself gets some current. But whenever this connection is removed, gate and drain between connection, so it has to be biased separately. For that one we are using V bias 2. The advantage of making this one is nothing but we can increase output impedance by a large amount, that we will see. So in that regulated cascode current sink, transistors M2 and M4, transistors M2 and M4 will form the negative feedback loop. M2 and M4 in Wilson current mirror also the same thing, M2 and M4 only forming the loop, and that negative feedback loop stabilizes I naught. Stabilization of I naught against variations in V naught. In the circuit diagram, V bias 1 and V bias 2 are constant voltages which are used to bias M1 and M3 transistors, so that current flows through M1 and M3 transistors are also constant. So ID1 is going to be constant and ID3 is constant. Remember that one. With the help of these two things, we are going to say I naught is stabilized. ID1 is constant and ID3 also constant. Now, if I naught try to increase, whenever V naught try to increase, by that time that forces I naught to increase. Whenever I naught increases, at that time VDS4 is reduces because ID3 is constant. Current flowing through this M3 is constant, so that this I naught cannot change. But whenever V naught increases, that forces more current. That more current is specified in terms of reducing the drain to source voltage of M4. so that at lesser drain to source voltage you are getting a larger currents. That is the meaning. So as V naught increases, I naught try to increase. By that time that forces VDS4 to decrease. VDS4 is decreasing is nothing but that reduction in voltage is going to be increases at point A. So that total voltage is nothing but V naught. So VDS4 is reduces. So more voltage is dropping across M3 drain to source, that is VA. So as I naught increases, VDS4 decreases because ID3 is constant and VA increases. Whenever VA increases, VA is nothing but gate voltage of M2, so that it will make ID2 to increase, current flowing through M2 to increase. So that makes ID2 to increase, but ID2 is nothing but it is coming from M1. Current flowing through M1 is ID1, which is constant, so that ID2 cannot increase. Whenever ID2 cannot increase, that increase in ID2 is specified in terms of reduced drain to source voltage across M2, so that when ID2 increases, at that time VDS2 try to reduce. VDS2 is reducing is nothing but voltage across point B is reducing. Voltage at point B is nothing but gate voltage of M4. So VG4 is reduces. Whenever gate voltage reduces for M4, corresponding drain current reduces in saturation. So that even I naught try to increase, that increase is compensated by reduction in I naught. So this is the loop followed by M2 and M4. As I naught try to increase, that will be compensated so that I naught is stabilized. Next, calculate output resistance R naught. Again the same thing. Draw the small signal model equivalent and apply a test voltage across output terminals, which results in test current. Get the ratio of test voltage by test current, that gives the output impedance. Out of this regulated cascode current sink, there are 4 transistors. Out of the 2 transistors M1 and M3 are constantly biased with V bias 1 and V bias 2, so that a constant currents will flow ID1 and ID2, so that they can be modeled as a constant resistor, so that replace M1 and M3 with R01 and R03. First point. Next, replace the remaining transistors M2 and M4 with equivalent models. While going with that one, M4 is going to be modeled along with body effect, whereas M2 doesn't have any body effect, because M2 transistor source is connected to VSS, whereas M4 transistor source is not at VSS, it will be at some other voltage. So definitely there is a source to bulk voltage present in case of M4, that causes body effect. So this is the equivalent circuit of regulated cascode current sink. After incorporating M1 and M3 replacing with R01 and R03, and VDD and VSS are shorted to ground. Next, M4, M2 and M4 are modeled with small signal equivalents. While modeling M2, there is no body effect. While modeling M4, there is a body effect. If you observe the small signal model of regulated cascode current mirror and Wilson current mirror, both are exactly similar except for one difference, that is M3 was diode connected previously, that's why over here this resistor was not R03, by that time that was 1 by GM3, and now here it is R03. R03 is very large, whereas 1 by GM3 is very small. Because of this change, we will get more output impedance in case of regulated cascode current mirror. If you analyze this circuit with equations, at that time you will get the output impedance as the ratio of Vt by It. So this is the final expression you will get. And if you observe this one, R04 is multiplying this term gm into R0, so that the effective value is gm into R0 square if you assume identical transistors. That gm into R0 square is again multiplying with this term, that is gm into R0 by 2. R01 parallel R02, if it is identical at that time, R0 by 2 you will get. So gm R0 square multiplied by gm R0 square by 2. So this will be equal to gm square into R0 cube by 2. This is gm R0 square multiplied by gm into R0 by 2. So that the effective value R out is equal to gm square into R0 cube by 2. So remember, recollect the value of output impedance of Wilson current mirror. It is gm times of R0 square by 2. There is only gm, that was not gm square, gm into R0 square by 2, and here gm square R0 cube by 2. It is very very large. If you assume typical values of GM transconductance as 20 microampere per volt and R0 as 10 megaohms, then R out is calculated to be 400 gigaohms, very very high, that can be approximated as ideally infinite. So only regulated cascode current mirror will give highest output impedance, which is towards ideal the value is. Because of this one, it is going to be giving V0 minimum as the least one, that we will see next. Prove that V0 minimum is less than other current mirrors. So calculate V0 minimum. Before calculating V0 minimum, what we concluded is output impedance of regulated cascode current mirror is the highest one, which is approximated as infinite, since it is gm square R0 cube by 2. And because of that one, R04 is assumed as infinite. And the same thing, R04 is nothing but output impedance, that is output voltage by output current. VDS4 divided by current flowing through it is nothing but I0. Output impedance is nothing but changes in VDS divided by changes in drain current. But I0 is stable because of negative feedback. So changes in I0 is taken as 0. So changes in VDS divided by 0 is nothing but infinite resistance. Infinite resistance is nothing but here VDS4, whatever the value of VDS4, since the change in I0 is constant, R0 is approximated as infinite. So voltage across VDS4 doesn't make any change in output current. Output current is not influenced by VDS4 much. So even though VDS4 is large or small, output impedance is infinite and I0 is going to be constant. So that M4 can be even non-saturated and still maintains a fairly constant current. M4 can become non-saturated, that is VDS4 is very less than VGS4 minus VT. That is a condition for non-saturation region, that is linear region. Even in that case also it maintains a fairly constant current. This is very very important. Generally in all other current mirrors, M4 must be in saturation, but because of high output impedance of regulated cascode current, we can make even M4 to come into linear region even though it is maintaining the same constant current. So that because of that one, if you take V0, output voltage of regulated cascode current mirror is VDS4 plus VDS3. Voltage across M4 plus voltage across M3 is nothing but total output voltage. V naught minimum is nothing but minimum voltage to keep I naught constant. So V naught minimum is nothing but VDS4 active plus VDS3 saturation. Even though M4 comes into active region, that is linear region, the current is going to be constant only, so that we are not making saturation, it can be in active region. So V naught minimum is VDS4 active plus VDS4 VDS3 saturation. VDS4 active condition for active or linear region, VDS4 is less than VGS minus VT. So VDS4 can be neglected. By that time V naught minimum approximated as VDS3 saturation. So VDS3 saturation is nothing but VGS3 minus VT, that is effective gate voltage of M3 transistor, that is nothing but overdrive voltage. A single delta V is sufficient for maintaining I naught constant in regulated cascode current mirror. So V naught minimum in case of regulated current mirror is single delta V, which is very small compared to other current mirrors. V naught minimum for Wilson current mirror and cascode current mirror is 2 delta V plus VT. So that V naught minimum is least out of all current mirrors discussed. Next, regulated cascode current mirror. This is a diagram till now we discussed, which is nothing but regulated cascode current sink, because there is no mirror action is taken place yet. We have not discussed anything about the mirror action. So I naught is independent of ID1. Look at this diagram clearly. ID1 is supplied with V bias 1, whereas I naught is going to be supplied with the help of V bias 2. So V bias 2 is supplying ID3, ID3 is equal to I naught. So I naught is totally depending on V bias 2, and ID1 which also flows through this ID2. So ID2 is depending on V bias 1. So these input current ID2 and output current ID3 both are going to be independent of each other. Since ID2 is controlled by V bias 1, ID3 is controlled by ID4 controlled by V bias 2, that is I naught controlled by V bias 2. So I naught and ID1 are independent of each other. They no need to be equal, or they no need to be maintaining any multiplication factor, since we are going with different biasing voltages. Now we will get, using this cascode current sink, we will get the mirror action by modifying this circuit. The modified circuit is this. If you check M7, M2, M4 and M3, these four are going to be looks like these four are forming regulated cascode current sink, and this is the extra things, these transistors. So V bias 1 is going to be provided with M6 and M5 combination, this one. So M6 and M7 are going to be treated as current source, which made up of PMOS transistors that produces a current. That current is supply independent, and that is flowing through M2. That is flowing through M2. So current flowing through M2 is biased by this M6 M7 current source. Next, M3 is biased with the help of M1 and M5. M1 and M5 current mirror. So that here it is M1, M5 and M3 all are going to be having equal VGS voltages. If M1 and M3 are identical, if M1 and M3 are identical, at that time ID1 is mirrored in M3. So I naught will be equal to ID1. The mirror action is going to be taking place, I naught equal to ID1. So we can get the input reference current as output current, and I naught is stabilized because of this regulated cascode current sink. Because of regulated cascode current sink, I naught is stable, and I naught is results because of input current ID1. So here mirror action is taking place and stabilization is with some other circuit. So both can be combined as a regulated cascode current mirror. So ID1 can be mirrored quite accurately through M3 if M1 and M3 are identical with same WL. Here ID2 not necessarily be equal to I0. So ID2 current flowing through M2 cannot be equal to I0. Even there is no relation, or it can be equal if M1 and M5 are going to be identical. So M1 M5 may not be identical, that is may not be in equal size, it may be having different size. That much current flows through this M6, that will be flowing through this M2. Look at this one. Let us assume M5 is going to be twice of M1, so that 2 times of ID1 flows through this M6. The same 2 times of ID1 is flowing through this M7, that is flowing through this M2, and it is nowhere related to I0. I0 is only related to current flowing through M3, that will be biased by VGS of M1. So that I0 is only results because of ID1, and ID1 is going to be providing bias current required for M2 also, but there is no relation I0 and ID2. Remember that one.